Alright, we have a lesson in the central limit theorem. CLT is an extremely important theorem in statistics. Before we start the central limit theorem, we have to review what the normal distribution is. So on my screen, I have review normal distribution. So what is x? X is a continuous random variable that follows. So this little curve means follow, or is normally distributed with mean equals to mu and standard deviation equals to sigma. The mu is the center of the bell curve. The sigma is the spread of the curve. All right. X is a random variable. So what is x in reality? X is you go outside, you collect a data. So that is x. Now, how do you standardize? Remember this normal standardization. So to standardize x, I am going to call this a raw score. And then z, I am going to call that a standardized score. To standardize, I must know what the mu is and what the sigma is, and they are called parameter. So how do we standardize? What is normal standardization? Maybe the words are too big for you. So let's say raw score. You take a test, right? You take a test, you get a score. So raw score is the score that you are holding on your hand. Standardized score is I am trying to compare your score to everybody else who took the same test. How good you are is how do you measure how good you are? You don't say I am very good because I am better than my friends. That is not true. To know how good or how bad you are, you have to compare yourself to everybody else. And then to compare your score, I have to grab your score and then plug it into my computation system. How do we do this computation? So to do this computation, first, I am going to take your score, which is x, and then I subtract the population mean, which is mu, and then I divide it by sigma. I am going to call this z. Z is a standardized score. If that is equal to 0, that means you are exactly on average. If that is equal to a positive, that means you are above average. If that is negative, that means you are below average. But you might ask me, hey, we don't need to do this. I can compare myself, which is x, to the mu to tell you below, above, or exactly on average. Well, that is true. How about how many standard deviation but below or above average? What if that is equals to 1.5? Past 1.5 means you are above average, but how much above? That is what I need to know. 1.5 means you are 1.5 standard deviation but above average. If that is a minus, that means you are 1.5 standard deviation below average. If that is equal to 0, that means you are exactly on average, right? So why do we need to do this? Because like every time you collect data, right? So if you are talking about score, you probably don't get big numbers. But if you are talking about, let's say, the amount of money in people's savings account, you are not going to deal with numbers like 25 or 50, right? You will deal with numbers like thousands or millions or 10,000s, those kind of numbers. So I don't want to deal with big numbers, small number, don't really want to care about that. I want to make things simple. So what I'm going to do is I take the raw score, subtract the mu, divided by sigma. So after everything is done, I have a standard normal distribution. So standard normal distribution. Let's just use DIST, standard normal distribution. What is standard normal distribution? Standard normal distribution means now the mean is equal to 0 and the standard deviation is equal to 1. So we have a bell curve, a normal curve. 0 is in the middle. So if you add 1 and subtract 1, you get the first 68%, right? The empirical rule. If you add 2 theta, then you get 95%. So that is negative 2. This is a positive 2. If you add 3 theta, 3 sigma, then you get 99.7%. So that is negative 3 and that is positive 3. We still have a little bit on either side. All right, so that is the review of normal distribution. But what about central limit theorem? Central limit theorem, so here is the thing. Now, let me change colors first. Okay, now, I have a population, and this is the distribution of my population. What is the distribution called? The distribution is called normal, right? So that is called normal distribution. Okay, now this is my normal distribution. I have my mu and then I have my sigma, right? Now I am trying to take samples. So let's say I grab a first sample from this population. I am going to call this N1. That is my first sample. N1 is the size of my first sample. And then this sample has a size. What else can I do? Every time I take a sample, it doesn't matter what the distribution is. What is a sample? Sample means you have many numbers. So let's say you have a swimming pool, a big swimming pool. You have thousands and millions of numbers in this swimming pool. N1 is you reach your hand into the swimming pool and then you grab a bunch of numbers. So that is your first sample. And then I don't care what the distribution is. One thing that I can do easily is I calculate the sample mean, right? You have a bunch of numbers on your hand. Why don't you add them up and then divide it by the sample size? All right, then you have your x1 bar. I'm going to keep doing this many times. So I'm going to have my N2, N3, N4, N5, and so on and so forth. I'm going to keep doing this. I'm going to keep grabbing samples from the population. So every time you grab a sample, there is a sample size. So we have x2 bar, x3 bar, x4 bar, and then x5 bar, so on and so forth. Now, what I need to know is, hey, now you have a bunch of x bars, right? Look at the blue picture right now. You have more than one x bar, right? Yes. Now, you have more than one x bar. What is the distribution of this x bar? How do you find the distribution? What is distribution? Distribution means spread. To find the distribution, we go back to the most fundamental way. We build a frequency table and then we construct a histogram to see if that is a symmetric, skew left, skew right, or uniform. So that's the most fundamental way to find a distribution, right? Okay, so we have x1, x2, x3, x4, x5. So the distribution of these x bars, more than one x bar, I call this a sampling distribution. What is the distribution of this x bar? Listen, the distribution of this x bar is normal with mean equals to mu, and then standard error equals to sigma divided by square root of n. So now, when you standardize, you are no longer doing x bar, you are no longer doing x minus mu divided by sigma. When you standardize, you have z equals to x bar minus mu divided by sigma over square root of n. Now, that brings you to the next question. The question usually people ask me, the next question is, hey, you introduce two formulas. One is z equals to x minus mu divided by sigma. The other one you have x bar minus mu divided by sigma over square root of n. Hey, when is the circumstances to use the n? When is the circumstances of not using the n? Well, let me answer that question. Read the problem carefully. If there is a sample size in there, then this is the right formula to use. So that is how you standardize. So in this situation, in the blue situation, you are no longer comparing x to everybody. In this, you are trying to compare x bar to everybody. So that is new in this section. Now, I have to tell you something more. We are not even close yet. So let me switch color for the next graph. I'm going to use pink. Now, another big what if. What if you don't know the distribution of the population? This one you know is normal, right? Look at the blue picture. You know it. You can see it. It is normal. What if the population is not normal? Or just don't say not normal. You don't know what it is. Okay, I got to draw another graph. So let's say we have another graph. So let's say we have something that looks like this. You have never seen that before, right? Do you know what the distribution is? No, you don't. And you are trying to guess, all right, I don't know what the distribution is, but if you ask me to locate the mean, I will say, all right, so sounds like mean is always something in the middle. Oh, okay, I get it. I will say that is the mean. Don't worry about this. I'm not going to say you are wrong. Now, the next step is I am going to take samples. So sample number 1, sample number 2, sample number 3, sample number 4, sample number 5, and then sample number 6. All right, and then for each sample there is a sample size n1, n2, n3, n4 to n6, right? And then you can keep going. Now for each sample, what is the basic thing that you can calculate? The basic thing I can calculate is I add up all the numbers and then divide it by n, right? So this is x1 bar, x2 bar, x3 bar, x4 bar. They are all in bars. Oh, by the way, in statistics, every time you put a bar on top of a letter, that means average. And then x6 bar. So and then so on and so forth. Now, what is the distribution of these x bars? What is the distribution? The distribution, the sampling distribution of these x bars is normal with mean equals to mu and then standard error. Or for standard error, from now on you can use SE, standard error equals to sigma divided by square root of n. But you might ask me, hey, hold on, wait, the population is not normal. You took a sample, all right, I get it, and then you calculate the sample mean, and then why you are saying that the sample means follow normal distribution? I don't really get it, because back to the blue picture, the population is normal, fine. You take some samples, fine. You have some sample mean, fine. You have a bunch of numbers, so these are taken from a normal population. All right, where you find the distribution is normal, I get it, but in the pink one, hey, I don't really get this. You took this from a non-normal distribution, or you don't even know what it is. Hey, why do you still say that that follows mean mu with standard error sigma divided by square root of n? Now, here comes with central limit theorem. Now, what is central limit theorem? So the central limit theorem, the CLT for sample means says that the sampling distribution of x bar is normal as long as the sample size is greater than or equal to 30. So as long as this sample size are greater than or equal to 30, the distribution of x bar is normal. Another way to say this is if, let me go back to pink. If n is big enough, so let's say n greater than or equal to 30, at least 30, the sample means has their own normal distribution, has their right? Their own distribution. You have a bunch of x bar, right? So if you grab all those X bar and then build a histogram, the histogram will look like this. So you have a bunch of X bars in here. The histogram will look like that. According to central limit theorem, as long as n is big enough, what is the mean? The mean is equals to mu, and then the standard error is equals to sigma divided by square root of n. So how do you do comparison? Let's say I grab a bunch of people and then the sample mean is X bar. How do you compare this X bar to everybody else? So here is how you do it. You subtract the mu divided by sigma over square root of n equals to z. So this is how you do normal standardization. The z, you can call that a z value, or you can call that a z score. All right, that is how you do it. So this is the concept of central limit theorem. So let me give you a summary before we move on. What does the central limit theorem tell us? The central limit theorem gives us information about the characteristics of this X bars right there, based on all samples of size n. So when n is sufficiently large, so let's say n is greater than or equal to 30, the central limit theorem tells us that X bars is approximately normal. So the sampling distribution of this X bar right here is approximately normal. So that's why I have a bell curve. The mean of this X bar, do you see there are tons of X bar? The mean of this X bar is mu. The standard error of this X bar, if you call that a standard deviation, I'm sure that is fine, but I prefer to call that a standard error, is sigma divided by square root of n. So that is the central limit theorem. So in the next video, I will show you some graphing technique and some graphs and then some calculator technique. So I will see you there.